This rotary rig has been on location for some time, drilling through layer upon layer of subsurface rocks on its way to a petroleum-bearing formation thousands of feet below. The topmost joint of a string of casing hangs stationary in the red casing elevators, showing that a casing string has been run and cemented in the hole. Now the drilling crew is waiting on cement. Moving below the surface, we can see the present situation. As labeled at top right, a string of 9 5/8 inch casing is cemented in 12 1/4 inch hole. This casing string isolates the formation through which the hole has already passed. The dotted line below the casing shows that still more hole must be drilled to reach the oil and gas. The hole must penetrate, as labeled at left, sandstone, shale, more sandstone and shale, a layer of salt, a layer of anhydrite rock, and finally a layer of dolomite rock that caps the gas and oil. When the drilling program was planned, the engineers and planners were concerned about the shale, salt, and anhydrite that had to be drilled through. They wanted to use a drilling mud that would allow a full-gauge hole to be drilled through the shale and was capable of drilling the salt and anhydrite without upsetting the mud properties. As the engineers studied the data, they also wanted to use a mud that offered maximum protection to the producing zone. In other words, they did not want the producing formation damaged by the mud. A previously drilled nearby well had shown signs of being damaged, and they didn't want a repeat of that. Here's what could have happened in the other well. Notice at left that the well bore is filled with water-based mud, shown in brown. Notice also, as labeled at upper right and shown in blue, that water filtrate, the liquid part of the mud, has invaded the formation, the pay sand in this case. A possible result is shown in the magnifying glass. There are particles of clay between the sand grains, and when the water filtrate contacts the clay swells. The swelling clay blocks up the passageways between the sand grains, and the oil, shown in green, cannot flow into the well bore. Or it could be that the water from the water-based mud invaded the producing sand and blocked off the flow of oil due to a surface tension phenomenon. Whatever the cause of formation damage in the other well, oil mud in the pits of this rig indicates that a change in the drilling mud was made. The oil mud should solve the production problem, as well as problems posed when drilling the shale, salt, and anhydrite. Let's take a closer look at oil muds. There are two kinds of oil muds, oil-base mud and invert-oil mud. Since in both types the liquid phase is mostly oil, any problems associated with water causing damage to a formation are minimized. Both oil-base mud and invert-oil mud contain some water. The water gives the mud viscosity or thickness, serves to control the amount of filtrate, the liquid part of the mud, that enters the formation, and is a carrier for certain other materials that are added to the mud. Since water and oil do not ordinarily mix, you may be wondering why the water doesn't settle out of the oil. Well, a photo taken through a microscope of an oil mud shows that the water droplets are emulsified in the oil. In other words, special chemicals called surfactants or soaps are added to the oil and water, and when the mixture is agitated or shaken up, the water is broken into small droplets and dispersed in the oil. The amount of water emulsified in the oil determines what type of oil mud is formed. An oil-based mud generally contains less than 5% water. An invert oil mud generally contains from 10 to 50% water. After making the decision to use the oil mud, it was decided to mix the mud at the mud company's liquid mud facilities rather than at the rig. Mixing could be done at the rig, but better mixing facilities were nearby and a more stable mud could be made. The mud engineer at the rig calls the liquid mud plant and gives them the information needed to mix the mud for the job. Back at the mixing plant, The liquid oil mud will be prepared and transported to the rig by tank trucks. Any additional treatment will be done at the rig as required. Several mixing pits at the plant, depending on the quantity of oil mud needed, are made ready to receive the oil. This tank holds high flash point diesel fuel. The diesel is piped from this tank to the mixing tanks. Crude oil could be used, but diesel is preferred to minimize the fire hazard from volatile components that may be in crude. Also, the diesel oil should have an aniline point above 150 degrees Fahrenheit. This minimizes damage to hoses and rubber pump parts on the rig. Aniline is a chemical that tells how harmful a diesel oil is to rubber. The aniline point is the temperature at which aniline and the diesel oil can be completely mixed together. The lower the aniline point, the more destructive is the diesel oil to rubber. Conversely, the higher the aniline point, the less destructive is the diesel oil to rubber. A basic oil mud ingredient is mixed to emulsify the water in the oil. The material also contributes to the viscosity, gel strength, and filtration control properties of the mud. Other supplemental emulsifiers and oil wetting agents are added to support the basic ingredients and to assure all solids stay oil wet during the drilling operation. These components are thoroughly mixed into the oil. A hose is connected to fill a separate tank with water. The water will be mixed later with the diesel oil. It may be brine water that is cut with fresh water to a predetermined salt concentration, or it may be fresh water to which calcium chloride or sodium chloride salt is added. The amount of calcium chloride, CaCl2, in the mud is very important. Calcium chloride is a salt, and it is used to make the water in the oil mud salty. Shale, like an oil mud, also contains water. A look into the magnifying glass to the right of the hole that is filled with oil mud shows that there is salt water in the shale and salt water in the oil mud. During drilling, the water in the mud comes in contact with the water in the shale. There is a tendency for the water in the mud to transfer to the water in the shale, or for the water in the shale to transfer to the mud. Water transfer in either direction depends on just how salty the water in the mud and the shale is. Water transfer in either direction is usually not desirable. Therefore, to prevent water transfer in either direction, the amount of calcium chloride dissolved in the water of the oil mud should be such that the water is just as salty as the water in the shale. If both are equally salty, then no water transfer occurs. Now let's stop for a moment to summarize. First, we saw that there are two types of oil muds: oil-base mud and invert-oil mud. Oil-base muds contain less than 5% water, and invert-oil muds contain from 10 to 50% water. Both types are made up mainly of oil, but other ingredients are added to give the mud viscosity, gel strength, and other desirable properties. The amount of calcium chloride dissolved in the water of an oil mud is important in order to prevent the water in the mud from transferring to the water in the shale, or to prevent the water in the shale from transferring to the mud. Once the proper amount of calcium chloride is dissolved in the water, this brine solution is turned into the tank containing the oil. To make a good stable emulsion, the water is added slowly to the oil with vigorous stirring. Tests, like this funnel viscosity measurement, are run as a check to make sure that the oil mud is properly emulsified and has the desired properties. Meanwhile, at the rig, drilling starts in the section below the cemented casing. Note that water-based mud is still in the hole. After drilling out a few feet, the blowout preventers are closed and the well is pressured up to test the cement job and to see if the formation can withstand the pressure without fracturing. If the formation does fracture, then mud flows out into the fractured formation and does not return to the surface. In other words, lost circulation occurs. Of course, lost circulation is never desirable. but it's especially bad with an oil mud because oil mud is so expensive. Other precautions should be taken when using an oil mud. Here, oil-resistant piston rubbers are being installed before the pump is put into service. Also, the valve rubbers of the pump should be oil-resistant. All other rubber components should be oil-resistant. For example, the rotary hose, the U-shaped line that carries mud from the standpipe at right and to the swivel at center. The mud engineer tests the viscosity and other properties of the water-based mud still in the hole. The water-based mud must be in good condition before it is removed and replaced, that is, displaced out of the hole. Its being in good condition assures better displacement. The tank truck carrying the oil mud from the mixing plant arrives at the rig. The mud is put into the pits through a hose after the water-based mud is emptied out of the pits. To begin the displacement of the water-based mud out of the hole, a freshwater spacer 500 to 1,000 feet long is pumped into the drill stem. This is followed by an oil spacer that is also 500 to 1,000 feet long. These spacers prevent contamination of the water-based mud and of the oil mud. Also, the spacers clean the hole as they are pumped around. Then the oil mud is circulated after the oil and water spacers are in place. Slow pump rates are used, and the drill stem is moved up and down and rotated to obtain a better displacement. The old water-based mud is disposed of into the reserve pit. Some of the good mud may be placed in storage for emergency use on this or the next well. Any commingled water and oil mud should be discarded. Before drilling begins with the oil mud, fine mesh shaker screens have been installed to help remove the finer cuttings from the mud. If the finer cuttings and solids are allowed to remain in the mud, they cause the mud to thicken and increase mud treating expenses. Also, the screens will be kept clean to avoid losing good mud over the end. Oil mud is expensive, so mud salvage is an important economic factor. Here, for instance, is a tray with a drain into which pipe is set back when coming out of the hole. It catches the mud draining out of the pipe and returns it to the mud system. From underneath the rig floor, we can see the bottom of the rotary table with the square Kelly extending down through the rotary and into the bell nipple. Notice that the top of the cylindrical bell nipple is flared to catch any mud that may spill out around the rotary and run down the Kelly. Often a bell nipple with an even larger flare is used. Once the mud is in the nipple, the mud is returned to the mud system and not wasted. The disc-shaped device around the joint of pipe in the center is a pipe wiper. The wiper, when placed in the rotary table, wipes mud off the outside surfaces of the drill stem when pipe is pulled from the hole. This, too, saves mud from being wasted. This crewman is closing a valve that is installed in the drill stem just below the Kelly. When the Kelly is broken out of the string so that a joint of pipe can be added, that is, when a connection is made, the closed valve prevents the mud in the Kelly from running out on the rig floor. Another way to save mud and keep the floor clean. The large yellow device is a mud saver, or as it's sometimes called, a Mother Hubbard. When a trip is being made, the saver is placed around the joint of pipe being broken out, and if any mud flows out of the pipe, the saver keeps the men cleaner and keeps the mud confined. Note the drain connection with the flexible hose. This drain is placed in a connection with the mud return line and returns the mud to the system. Here, a roof over the mud pits keeps rain out of the mud. This is necessary in areas where heavy rains may add so much water to the mud that the mud would thicken and require additional emulsifiers and chemicals to maintain good mud properties. Once again, let's stop to summarize. Certain precautions should be taken when using an oil mud. For example, all rubber parts that the oil mud contacts should be oil resistant. Install a fine mesh shaker screen to keep the mud from thickening. Use a pipe tray when making a trip to catch mud draining from the pipe. Use a pipe wiper to clean the outside of the pipe when coming out of the hole. Use a lower Kelly valve to keep mud from draining out of the Kelly. Use a mud saver to keep mud from splashing on the crewel and floor when breaking out a joint of pipe. Put roofs over the mud pits in rainy areas where too much rainwater would give problems. Once drilling with the oil mud is underway, it's important for the mudman to make frequent tests on the mud to keep it doing a good job. The derrick man should check the density or mud weight with familiar mud balance, and viscosity is tested with a marsh funnel. The funnel viscosity of an oil mud is usually higher or thicker than that of a water-based mud of the same weight. Mud companies usually use a special oil mud report form similar to this one because some of the tests are unique to oil muds. For example, an electrical stability meter is used to determine the emulsification of the water in the oil mud. Oil does not conduct electrical current, but by immersing the electrodes in the mud and increasing the voltage, current can be made to flow. The more voltage it takes to establish electrical flow, the more stable the emulsion. The API high temperature and high pressure filtration test is made on oil muds. This gives an indication of the mud's stability. Note the filtrate, the dark brown liquid in the glass cylinder in the engineer's left hand. It should be oil with no water. If water is present, then the mud is showing signs of instability and will have to be treated. Here, in a portable laboratory, the engineer is slowly adding an acid to the oil mud to check the mud's alkalinity. Out on the rig, lime is usually added to keep the alkalinity within the desired range. To check the activity of the mud, that is, to see if water is being transferred from a formation to the mud or from the mud to a formation, the relative humidity of the mud is measured with an electrohygrometer. If water transfer is occurring, additions can be made to the mud to stop the problem. All the tests show that our mud is behaving well. No hole problems have developed thus far, and the mud engineer is keeping close watch on the properties. But now the hole enters a pressured formation. As a result, the level of the mud in the pits begins to rise. Looks like we've got a kick. The driller closes the annular blowout preventer to shut the well in. Over at the pressure control panel, a worksheet is filled out with pertinent data necessary to kill the kick. Calculations show that the mud weight needs to be increased 0.2 of a pound to control the kick. The driller opens the choke control on the panel. The kick will be circulated out of the hole through the choke, and then the mud will be weighted up. As the kick nears the surface, a look at the casing pressure gauge at top right shows that the pressure on the casing is very low, a sign that the kick is salt water. If the kick were gas, the casing pressure would read a much higher value. And an examination of the mud in the portable lab shows it has a grainy appearance, the bright spots in the mud on the knife. Also, notice how the cuttings stick to each other and are gummy looking. This is an indication of water-wet cuttings. To overcome the problem of water wetting, the derrick man adds an oil wetting agent to the mud. After killing the kick, tests are again made to be sure the mud is stable and has the right chemical activity to drill the next shale section. As the hole enters the salt section, no adjustment of the mud properties is necessary to drill a near-gauge hole. If a water-based mud were being used, it's possible that the water in the mud would dissolve the salt and enlarge the hole. But since an oil mud is in use here, there's little chance for the salt to be dissolved in the water phase of the mud. The hole is quickly drilled through the anhydrite, dolomite, and into the pay sand with no problems. At total depth, the hole is cleaned up and the crew starts coming out of the hole. We will soon learn just how well the oil mud has performed to prevent damage to the pay zone. With the drill stem out of the hole, a logging truck is called out to the well. The well is logged to determine the best part of the pay zone to complete. Since the oil mud is non-conductive to electric current at voltages normally used for electric logging, usually a radioactive or sonic log is run. After the log is interpreted, a liner is set from the 9 5/8" casing through the pay section. With the liner run into the hole, a cementing company arrives on the scene. Cementing casing with an oil mud in the hole is a little more troublesome than with a water-based mud. Oil muds are thickened by solids, and cement has a lot of solids. Since a good cement job could not be obtained if the mud thickens, diesel oil, surfactant, and a non-swelling clay is run ahead of the cement to keep the oil mud and cement from mixing together. A cement bond log shows that the cement job is a good one, and that the top of the cement is above the point where the saltwater flow was encountered, thus offering protection from casing corrosion there and through the salt bed. Above, the oil spacer in mud is used as a packer fluid, providing casing protection from bacteria and corrosion that might otherwise occur in that section. The liner is perforated opposite the pay section and finally tested to determine if it's a producer. The company man tells the pusher that the well tests out okay, and from all indications shows no blockage of the pay. So it looks like the oil mud has served its purpose well. In summary, frequent tests should be made on an oil mud to make sure it is doing a good job. Weight is checked with a mud balance, while funnel viscosity is taken with a marsh funnel. Other tests indicate the mud's stability, alkalinity, and activity. If a saltwater kick is encountered, oil wetting agents may have to be added to the mud. Finally, radioactivity or sonic logs are used in holes filled with oil muds because oil muds do not conduct electric current at voltages normally used in electric logging. From the thousands of routinely drilled wells to the latest ultra-deep holes, the application of oil muds is one more way of obtaining much-needed hydrocarbons for today and the future.